Okay, good morning. Today we're going to be talking about Module 10, periodic motion. And so just like I did in class, I pulled out some of the equations. He goes through a lot of derivations in the chapter, and I don't want you to get lost in the math there. But these are the equations that we're going to use for Chapter 10 for periodic motion. And in this video, I'm going to talk a little bit about those equations and what they mean. So of course, whenever we're talking about physics, we can always come back to FMA. Force equals mass times acceleration. And in this chapter, we're talking about periodic motion, specifically dealing with weights on a spring or weights on a string swinging back and forth as a pendulum. So Robert Hooke is the one who did a lot of work in this area, and so he has a law named for him, and Hooke's law says that force equals the negative of the spring constant times the displacement of the mass on the spring. And so let's look a little bit about that. We know that force is in newtons. And so what is a spring constant? A spring constant tells us how stiff a spring is or how much force we're going to need to move it. So that'll make sense when we talk about how much it can be displaced. So when we look at a displacement, and we can see that the spring constant is negative because, remember, in most of the time in physics, our positive and negative signs are talking about a direction. So the direction that the spring constant and the displacement is in opposition to the force applied. So if I have a spring and it's normally at rest like that, and I apply a force to stretch it farther, this will be our change in displacement, and from our equilibrium point to as far as we stretch it. So we had to apply a certain amount of force to get it to stretch this amount of displacement. And so the Hooke's constant or the spring constant tells us how much force we need to apply. You guys, when we passed around the springs in class, some of the springs were easier to pull apart and some of them required much more force. So this is the law that tells us how to find that amount of force. And so the spring constant only has to deal with the actual spring of the time. Each spring has a different spring constant or Hooke's constant. So we'll talk about the units again. Newtons are a unit of force, and we know that meters are a unit of distance. And so if we rearranged this equation to solve for the units here, we would try to get the spring constant alone. So we would leave it there on this side of the equation, and we would take his friends away. We would divide both sides by change in x. So we would end up with force divided by the change in distance equals our spring constant. And so we would have our newtons divided by meters. And those are the units for our spring constant. So there is that one. So those are going to be pretty straightforward questions. In the text, they'll say things like, I have a certain length of spring and it has a spring constant of a given value. How much force is required? So it would be a straight plug and chug question for those kind of things. The only trick to those questions are sometimes they will give you maybe the equilibrium of a spring. Say this spring is 8, and in the book he tends to do it in centimeters, so you're always going to have to convert to meters. So it would be 8 meters is our spring in equilibrium. And then you could say, oh, they stretched it so that the spring then had a length of, say, 15 centimeters. I'm going to convert it right away. So 0.5 meters. Remember, anytime that we want to find a change in something, it would be the final minus the initial. So just like for change in momentum, change in velocity, change in acceleration, anything that has a change in it, final minus initial. So this is our total length, our total final length of the spring. And so it would just be 0.5 meters minus our initial, and so we would have a change of 6.7 meters. So that's the only kind of tricky part that they would have in these kind of questions. So just be sure that you are understanding what they're asking for. Okay, so let's look at the second equation. The second equation looks a little messy, but often when we talk about periodic motion, we talk about things bouncing on a spring or swinging back and forth at a pendulum. They talk about two different values. They talk about the period of the motion, or they talk about the frequency of a motion. And we'll get more into frequency on chapter 11 when we do waves. But for now, we're going to talk about the period. How much time does it take to go through one cycle of that motion? And so our period, we're given this equation that the period of something on a spring is 2 times pi times the square root of its mass divided by its spring constant. Now you notice the spring constant is not negative here because it's not talking about a direction. It's talking about the period, or how much time it takes.